Section 10.5 discusses what are called parametric equations. So parametric equations are a set of equations that relate two variables, usually x and y, to a third variable called the parameter. What that really means is we're going to take functions that we've been dealing with, so y equals something in terms of x. That's an equation that relates x to y. Parametric equations are when x and y are separately related to a third variable. So that third variable could be t, that represents time, could be theta, which represents an angle. That third variable can really be any variable, but really the idea is that we're going to be able to express x and y separately, which allows for some different applications for graphing, ways to describe motion of an object or a point along a curve. So parametric equations is just another way to approach defining quantities in terms of a third variable, oftentimes what we're going to talk about, time. So for example 1, we're asked to draw the graph of each set of parametric equations using the given interval, which we have x equals 2t plus 3, y equals t plus 2, and the interval is from 0 to 3 for t. And then after we draw the graph, we're going to eliminate the parameter. What that really means is take our parametric equation and rewrite it as what's called a rectangular equation. What all that means is an equation y related to x. So y equals something in terms of x, which will be a function that we're used to seeing up to this point. So to graph this set of parametric equations, at least for now, we can make a table for the parametric equations. So t is going to be our parameter, and x and y are going to be related to t as given in those equations. So to make a table, I'm just going to pick values from 0 to 3 for t. So 0, 1, 2, 3. And then to find x and y at those time values, you just plug those t values, sorry, not necessarily time, but a lot of context it is time, but plug those t values in for x equation and in for the y equation. So at 0, I would get 3, 2. At t equals 1, I would get 5 for x and 3 for y. At t equals 2, I'd get 7 for x and 4 for y. And at t equals 3, I'd get 9 for x and 5 for y. So that's a table that allows me to take values for t on a specific interval and then get x and y values at specific t values. Now, the way you're going to graph that is, now you can see we have an x value and a y value. That's a coordinate. That's an ordered pair. So if I want to come up with a graph, I would just plot these points, and what you'd see is it's going to create this set of parametric equations is going to create a line segment. Now, I do want to be clear. It is a segment because since t is on a finite interval from 0 to 3, then my graph should start and stop at the x and y values that correspond to the interval 0 to 3. So there's the graph of my set of parametric equations. And what you might see right there is, well, that looks like a line. I might be able to write that as an equation, a linear equation, and that's what we're going to do by eliminating the parameter. So what that means is I'm going to try and take these equations expressed in terms of t and rewrite them as one equation that relates x and y. So typically what I'm going to do is look at the two parametric equations and see which one would be easiest to isolate t. And y equals t plus 2 is definitely easier to get t by itself. So now I have t in terms of y, and then to eliminate the parameter means my final answer shouldn't be an equation that has a t in it, which is our parameter here. So what I'm going to do is take y minus 2, and I'm going to replace that for t in my x equation. So I do that to get x equals 2 times the quantity y minus 2 plus 3. Distributing, I'd get x equals 2y minus 4 plus 3, so x equals 2y minus 1. And that right there is a rectangular equation. So that's an equation in terms of x and y. But I'm going to rewrite that and get y by itself just because we're a little bit more comfortable seeing it that way. And then we're going to basically verify that that rectangular equation I come up with should be the exact same equation I got in my graph or my parametric equation. So multiplying or dividing both sides by 2, I'd get 1/2 x equals y minus 1/2, and then add 1/2 to both sides. I get y equals 1/2 x plus 1/2. And then to verify, if I graphed y equals 1/2 x plus 1/2 and restricted the x values from 3 to 9, I'd get the exact same graph I got with my parametric equations. So that's sketching a parametric equation using a table and then using some algebra to rewrite this set of parametric equations in terms of x and y, or the language there would be a rectangular equation. So for example 2, we're going to do something very similar in terms of sketch a parametric equation by making a table and then eliminate the parameter algebraically so that I have a rectangular equation, or an equation in terms of x and y. So one thing I want to point out right away is our parametric equations are 3 cosine of t for x and y equals 4 sine of t. So I'm going to make the table, sketch the graph, and then we'll talk about the algebraic approach to eliminating the parameters. So here, make a table. So I'm going to go from 0 to pi, and I'm going to put a couple values in between, 0, pi over 4, pi over 2, 3 pi over 4, and pi. And then just plug those values in for my x equation and my y equation. So when t equals 0, I get 3 for x and 0 for y. And then at pi over 4 and 3 pi over 4, they're not going to work out to be, nice numbers. I'm going to leave them in terms of radicals, but it will be a good idea to kind of have an idea of what that number is as a decimal. And you'll see when we graph why that's necessary. So at pi over 4, so cosine of pi over 4 is root 2 over 2 times 3, which is 3 root 2 over 2. And then for y, I should get 4 times root 2 over 2, or 2 root 2. So that's the x and y values at pi over 4, and at pi over 2 I should get 0 for x and 4 for y. And then at 3 pi over 4 I'd get negative 3 root 2 over 2, positive 2 root 2 for y. And then at pi I'd get some nicer values. I'd get negative 3, 0. So I want to try and plot those points, x, y, on my x, y axis, or my rectangular axis, and then see what the shape of this parametric equation looks like. So make my x, y axis here. And now when I said before, it might be a good idea to have an idea of what 3 root 2 over 2 is as a decimal. It's about 2.2-ish. A way I do that is root 2 is about 1.4. Divided by 2 is about 0.7-ish, something like that. And then times 3 is about 2.1 something, 2.2. And then 2 root 2 would be about 2.8-ish. And those are, again, decimals. I don't have my calculator with me, but they're right around 2.1 something and 2.8 something. And the reason why I say that is just to know where to plot that point. So 3, 0 is easy to plot. And like I said, it's like just past 2 and almost up to 3 as a y value. And then at 0 I get 3. And then those values are symmetric over the y-axis. So if I plot those, you might be thinking, like, how do you know to connect it that way? How do you know that it's going to make a nice arc there? And what you could do to verify is check some more values in between, and what you see is it makes kind of this arc shape there. Hopefully you're recognizing that is not a semicircle, right? The y value from 0 to 4 and the x value from 0 to 3, they're not the same. So it's not half a circle, it's actually half an ellipse, and we'll verify that here in a second algebraically. So that is the graph of, or a sketch of the graph of the parametric equations. Now in terms of eliminating the parameter, I'm going to do something similar as I did before, try and look to get t by itself. But the problem is, if I divided both sides of the x parametric equation by 3 and the y equals 4 sine of t by 4, what you'd see right here is I have cosine of t, and there's really no nice algebraic way to get t by itself. Now I don't want to take the inverse cosine because I'm not trying to find a specific angle. I really want to express t in terms of y or x. So here's where a trig identity comes into play. What you might remember is cosine squared of t plus sine squared of t is equal to 1. That's our Pythagorean identity. I'm going to rewrite it as cosine of t quantity squared plus sine of t quantity squared equals 1. And the reason I would do that is I have an expression for cosine of t in terms of x, and I have an expression for sine of t in terms of y. So I can replace that cosine of t with x over 3, and I can replace that sine of t with y over 4. And when I do that, that's equal to 1. I would square that fraction, so I get x squared over 9 plus y squared over 16 equals 1, and that is our rectangular equation for this set of parametric equations. And if you think back to the very, very beginning of the school year, that equation should look familiar. That is the equation for an ellipse. And if you look at the graph, that is the top half of the ellipse. So then relating them, if I did x squared plus 9 over y squared plus y squared over 16 equals 1, the restriction for x would be, the domain for this parametric equation would be negative 3 to 3, and you can also verify that looking in the table. If I'm going from 0 to pi for t, the domain is from negative 3 to 3 for x. So the rectangular equation for this set of parametric equations would be this equation of the ellipse, but I would have to have that domain restriction because my parametric equation doesn't go beyond negative 3 and 3 for the interval that I was given. It could, if I was given a different interval or not given a specific interval, I would have to graph more, but because I'm limited from 0 to pi, I do have to match that with the domain restriction for my rectangular equation. And I'm just going to write that's an ellipse and then just kind of just draw an arrow there just to verify that. So for example 3, what we're asked to do is find a set of parametric equations for each rectangular equation. So now we're not trying to eliminate the parameter, we're trying to go from a rectangular equation to a parametric equation. So for this first example, y equals 2x squared minus 3. I want to rewrite x and y both in terms of a third variable called our parameter. Oftentimes, especially in this case, you might just be able to define one of your x or y variables as your parameter. What I mean is, because this is y equals 2x squared minus 3, if I said that x is t, so just defined x parametrically as t, then that means I can rewrite y in terms of t as well. So if I did replace the x in my equation with t, y would be equal to 2t squared minus 3, and those would be a parametric way to define this rectangular equation. Now, just saying x equals t, you might be thinking, well, how do I know to do that? Why does that work? You could say y is t, right? You could define y to be t, but then you would have to say t equals 2x squared minus 3 and then solve for x. So it's convenient to pick the variable that allows me to write my second parametric equation in terms of that parameter. So in this case, defining x to be t allows me to rewrite y very easily in terms of t, and then I have my parametric equation that I was looking for. For the second example, it is going to be a little bit different, and what I mean is, looking at that, if I just said x is t or y is t right off the bat, it's not going to give me an algebraic way, a simple algebraic way to write the other variable in terms of t. So what I'm going to do first is I'm going to try and rewrite this equation so that it looks something like what we did in a previous example, or like an equation that we've dealt with before. What I mean by that is if I were to divide everything by 9, okay? If I divided everything by 9, what I would get is x squared over 9 plus y squared over 9 equals 1. And then that looks a lot like the Pythagorean identity. So what I'm going to do is kind of rewrite this and try and get something squared plus something squared. So if I rewrite x squared over 9 as x over 3 quantity squared plus y over 3 quantity squared equals 1, that is the Pythagorean identity. Something squared plus something squared equals 1. So x over 3 I can call cosine of t, and y over 3 I can call sine of t. So I'm going to do that. So cosine of t is x over 3. Sine of t is y over 3. And then in terms of writing x and y in terms of t, I would just have to multiply both sides of each of these by 3. And what I'd get is 3 cosine of t equals x and 3 sine of t equals y. Now I do want you to think for a second what this graph would look like. If I plugged values in for t, I'd have to have a specific interval or think about what this looks like. But if I look at my original equation, x squared plus y squared equals 9, that's a circle. That's an equation for a circle, centered at 0, 0 with a radius of 3. And then if I look at my parametric equations, 3 cosine of t, 3 sine of t, that looks x equals some number times cosine of t, y equals some number times sine of t. That looks, hopefully to you, looks a little bit like our unit circle definition. The only difference is that 3 out in front is really representing the radius of our circle. So if I were to plug angles in for t, I would get coordinates moving around a circle, which makes sense if we think about how the unit circle is defined and how that's related to our rectangular expression of a circle, x squared plus y squared equals r squared. So that's just kind of a way to verify that those kind of make sense. You could make a table of values and see that the interval for t, if you really were asked for one, would be the one that would make the most sense would be 0 to 2 pi, since this does represent a circle for your parametric equations and for your rectangular equation. For example 4, we're given two graphs and we're asked to find a parametric equations for the graph and then give minimum and maximum values for t for our parameters. So the first thing I'm going to do for this ellipse graph is I'm going to write this equation as a rectangular equation. So doing that, I would identify the major and minor axis. Hopefully this vocab is ringing some bells. So the major axis would be the larger one, the longer one, which in this case is along the x-axis, so that's A. And the minor axis would be vertically from 0 up would be B. So A is 4 and B is 2. So then if I want, and the center is 0, 0. So if I want to write this equation as a rectangular equation, I would get x squared over 4 squared plus y squared over 2 squared equals 1. Or x squared over 16 plus y squared over 4 equals 1. Remember, A is the larger axis which goes under x because x, it's wider from left to right. Hopefully that's ringing some bells. And then right here, instead of writing 16 and 4 in the bottom, I'm going to try and write this as something quantity squared plus something else quantity squared equals 1. So x squared over 4 squared is really x over 4 quantity squared, and y squared over 2 squared is really y over 2 quantity squared. And then I can rewrite x over 4 as cosine of t and y over 2 as sine of t, which then if I solve for x and y, I would get my parametric equations for x and y. And then thinking about the interval, the t min, t max, so all that's saying is the interval for interval for my parameter. The one that makes the most sense to me, thinking about this graph rectangular, it's an ellipse, but if I look at my parameters or my parametric equations, the values that makes the most sense for t is 0 to 2 pi because I want a complete revolution around this figure, which means I would want cosine and sine to pass through a full period to create this graph. And a little bit later we'll look at an example where we put these parametric equations in our calculator and kind of verify a shape like this. So the t min and t max in this case would be 0 to 2 pi because that would represent a full period of cosine and sine in this ellipse graph. For the second example, we have a line segment. I put the dots there on the end just to show that it was a segment. So the first thing I'm going to do is write this as a rectangular equation. So I'm going to find the slope and the y-intercept. So the slope is going to be -1/2 and the intercept is going to be 2. So I have my rectangular equation for this graph, and now I want to rewrite this as a set of parametric equations. So I'm going to name one of my variables as my parameter and then use that to rewrite my other variable in terms of that parameter. So the easiest one, because y is expressed as a function of x, is if I say x is t, So I'd call x my parameter, then I can rewrite y as negative 1/2 times t plus 2, which is y equals negative 1/2 t plus 2. So my set of parametric equations for this graph would be x equals t and y equals negative 1/2 t plus 2. So for example 5, we're going to look at how to graph a set of parametric equations for a given variable in your calculator and then sketch that graph by hand. So my parametric equation for x is 2 cosine of t, and for y I have 4 sine of t, and I'm going to be looking from 0 to 2 pi. For example 5, we're going to look at how to graph parametric equations in our graphing calculator. So the first thing we'd have to do in order to graph parametric equations is change our mode. So if you go to mode, you look down, below radians, it'll say function, and next to that, it'll say parametric. And what that's going to do is allow me to change my calculator mode to parametric, which means when I go to graph, I'm going to be looking for x and y expressed as a third variable. And in this case, it's going to be t. So what I mean by that is if I hit y equals, instead of these being y1 equals a function of x, it's going to be asking for x and y in terms of t. You'll see that's what that little t denotes right there, is I'm going to express my x and y in terms of my parameter, which is t, and then allow me to graph from there. So for example 5, our x parameter, or our x equation is 2 cosine of t. Now if I hit this variable button when I'm in function mode, that gives me the variable x, but because I'm in parametric mode, it'll automatically give me the variable t. And then for my second parametric equation for y, I will type 4 sine of t. And you could hit graph right here, but the one thing you do want to adjust is your window, because we're given a very specific window for t. I want my t min to be 0. I don't know exactly what your default number there was, but I want it to be 0. And then I want my t max to be 2 pi. So second caret gives me pi. When you hit down, it's going to automatically change that to a decimal, but that's approximately 2 pi. And then these x mins and x max, that's really going to give me, my regular viewing window in terms of x and y. So I don't necessarily know what to change these to right now, because I, again, don't necessarily know what this parametric equation is going to look like. So I'm going to leave them alone right now. I can always zoom in or zoom out or adjust those in a little bit. So once I have my parametric equations typed in for x and y, and I've adjusted my window to match my t min and t max values, I'll hit graph, and it should give me the graph of the parametric equation. What you'll notice this is a graph of is an ellipse. I know it's an ellipse because from 0 in the x direction, that is 2 this way and 2 that way, and this is 4 this way and 4 that way, which were not coincidentally, the coefficients of my cosine and sine in my parametric equations. So the advantage to expressing x and y in terms of a third variable is this is not a function. So to type an equation of ellipse in function mode is very, very difficult. You'd have to solve for y and have 2 separate equations to get the top half and the bottom half of this ellipse. But when x and y are expressed as a third variable, in this case t, it gives me a lot more freedom in the things that I can graph. I can graph conics, you can graph things that aren't functions at all, and it's simply by allowing x and y to be expressed as a third variable, your calculator will do a lot of that work for you. So then once I have an idea of what this looks like parametrically, I'm going to draw the shape here. My x-axis is going to be split up from -2 to 2, and my y-axis from -4 to 4. And then what we saw in the graphing calculator was that the shape of this graph is an ellipse that's wider from top to bottom or vertically. So the shape of it should look something like this. I'm going to draw it dotted first just so I can kind of get the shape down a little bit better. And then I'm just going to connect it here. So the advantage to using parametric equations here, again, like I said, is to be able to see a graph of something that is not a function. So an ellipse is not a function, doesn't pass the vertical line test. So parametric equations allows me to graph things like this a little bit easier instead of having to go through and solve for one of the variables algebraically and do a lot of that stuff. So this is what the shape of this set of parametric equations looks like.